Hi, I'm Kaz Garamukari, PhD student in National Institute of Informatics in Japan. Today, I'm going to talk about my current work about low-rank approximation with information geometry. Low-rank approximation is a popular method to extract features from table data. In this task, we approximated data with a linear combination of bases to extract features. The bases often are called principal components or factors. Nowadays, non-negative constraints on these approximation has important role because of its interpretability. But once we impose non-negativity, the optimization is often based on gradient method, which needs tuning for stopping criteria, running rate, and initial values. In this study, we propose novel methods to avoid these tunings. Let me show you our strategy. First, we capture data structure with DAG, and we regard input data as a probability mass function on that. The distribution is characterized with theta. And then we construct a low-rank subspace by describing low-rank condition with theta. Finally, because of well-developed projection theory in information geometry, we can find the projection destination without gradient method. Since there are so many variations of low-rank approximations, we now focus on the following two topics. The first one is about Tucker rank reduction. Let's consider a tensor P whose size is I times j times k. In this presentation, tensor means just multidimensional array. When the tensor is represented by three matrices A, B, C, and L times M times N quadtensor G, we say the rank of the tensor is LMN. In my presentation, we refer to a rank 111 tensor as a rank 1 tensor. We now want to approximate a non-negative tensor P by low-rank tensor P bar. This task is called non-negative Tucker rank reduction. We developed a faster rank reduction method called LTR. The second topic is developing faster algorithm for rank 1 NMF with missing values. The rank 1 approximation finds the most dominant factor. We find a solution rapidly using the known relationship of this task and coupled NMF. Okay, this is the contents of my presentation. And the first part is about LTR, and the second part is about NMF with missing values. Before diving into the main parts, we need to introduce how to treat a various data structure. As we have already explained in the strategy, we regard input data as a probability mass function on DAG. So first of all, we introduce a model on DAG. For this purpose, we use log linear model on DAG. This is a generalization of Boltzmann machine, and designing a DAG enables us flexible modeling. A finite set S is called DAG or poset if any element of S has reflectivity, antisymmetry, and transitivity. We define the log linear model on DAG S as a mapping from S to the open interval from 0 to 1. Natural parameters describe the model. We can also describe the model by expectation parameters if we use Möbius function. A distribution is uniquely identified by the determinant ether theta or eta parameter. That is, each point in theta space and eta space correspond to a distribution. Designing proper DAG, the model can handle with various data structure. Now we introduce the log linear model on DAG. So next, in the following slides, we will introduce a DAG to treat a tensor. Then we can discuss a tensor as a probability distribution. And after that, we will formulate tensor rank approximation from the view of information geometry. And next, we generalize a discussion to rank R approximation. Okay, so let's see the correspondence between probability and tensor. Let me repeat that in this presentation, a tensor means a multidimensional array. To treat tensor as a probability distribution, we assume that total sum of the given tensor is 1. We consider 3 times 3 times 3 tensor and make a mapping to a DAG. Each element on the DAG has an index, and the sketch shows the order relationship among them. This is a log linear model on this DAG. Each node in the DAG has natural parameter theta and expected parameter theta, eta. They distribute the distribution. For example, we focus on the element on 1, 2, 2. By the definition of the model, P122 can be described as this form using a natural parameter, which are smaller than 1, 2, 2. We can also describe P122 with eta parameter. Theta and eta are identified such that the value of P122 becomes the value of the tensor on 1, 2, 2. This is a mapping from tensor to a distribution. We regard a tensor as a joint distribution where the value of each element is the probability of realizing its index. The index corresponds to random variables, and the index set is the sample space. Now we have finished setting up the model, so then let's move to low-rank approximation. We define the theta and eta on gray node as one-body parameter, and other parameter as many-body parameter. And then we can prove that the tensor is rank 1 if and only if all the many-body theta parameter are 0. That is, rank 1 approximation is a projection onto a subspace whose many-body theta parameter are 0. The subspace is E-flat, which guarantees that the projection destination always exists uniquely. Then we can perform this convex optimization using the natural gradient method. However, the gradient method needs stopping criteria, running rate, and initial values. To avoid these tunings, let's describe the rank 1 condition with eta. We can show that if the rank of the tensor is 1, then the many-body eta can be factorized in this way. This is an eta representation of the rank 1 condition. Using these two representations, we derive a solution formula of the best rank 1 approximation. In the following slides, eta is expectation parameter of input tensor, and eta bar means the eta parameters after the projection. We will show all of eta bar can be obtained from eta. Let's see that. We perform the projection that make all of many theta 0. In this projection, one-body eta parameter do not change. It means that the value of one-body eta bar is the same as one-body eta. Let's see the eta representation of the rank 1 condition to find the value of many-body eta bar. After the projection, we can describe eta bar as this form. And the right-hand side is one-body eta parameter, which does not change in this projection. So we can write this formula. This is why all eta bar can be obtained from eta. Now all eta bar are identified. Using Möbius inversion formula, we found the projection destination in a closed form. From the next slide, we will discuss a projected point P bar. The closed formula of the P bar is simple. The best rank 1 approximation is a Kronecker product of summation in each axial direction. Although the best rank approximation for minimizing Frobenius norm is NP-hard problem, we can get the best rank approximation for KL divergence in polynomial time. Actually, the result has already been shown in AC/SSA 2017. Our discussion reproduces their result using information geometry. Let's focus on the summation in each axial direction. We can find a normalized vector that depends only on index I, J, and K. A tensor with D indexes is a joint distribution with D random variables. Thus, a vector with only one index is an independent distribution with only one random variable. That is, rank 1 approximation approximates a joint distribution by a product of independent distributions. Approximating a joint distribution by a product of independent distribution is called mean field approximation. Mean field approximation appears often in physics as a methodology for reducing a many-body problem to a one-body problem. Let me share more geometrical understanding of that point with us. To understand the geometry of rank 1 approximation, I will explain the mean field approximation of Boltzmann machine. This is a Boltzmann machine. The first term is called bias or magnetic field, and the second term is called weight or electron-electron interaction. Mean field approximation approximates joint distribution by a product of independent distribution. As you can see, if all values of the weight are zero, the Boltzmann machine can be described as a product of independent distributions. So mean field approximation for Boltzmann machine is the projection that make the weight term zero. However, this M projection is usually impossible because the computing the expectation value needs huge computational complexity. So physicists often use mean field equation to optimize inverse K divergence instead of the impossible M projection. The projection is E projection, but the target submanifold is not M flat, so the E projection is unsustainable. In our modeling, if we focus on the correspondence between many body parameters and the weight of the Boltzmann machine, we can find an analogy. In both tasks, we project given data onto a manifold to approximate it as a product of independent distributions. To reach the manifold in Boltzmann machine, the weight term required to be zero. On the other hand, in Lancôme approximation, many body theta parameter required to be zero. But in our case, the sample space is much smaller, and we can know the value of the expectation value in polynomial time, which enable us to perform M projection. That is, Lancôme approximation is a mean field approximation without mean field equation. I hope this table makes the resolution clear. Lancôme approximation and mean field approximation of Boltzmann machine are projections onto E-flat subspaces. But in Boltzmann machine, then projection is impossible. So we use mean field equations to optimize inversion K divergence. But in Lancôme approximation, we can find a closed form and it's computable because of the smaller sample space. Okay, we discussed the Lancôme approximation of non-negative tensor and its geometrical comprehension. Based on the discussion, we introduced rank-R approximation method called Legendre-Tucker-Rank reduction. First, we try to formulate a general Tucker-Rank approximation by relaxing the Lancôme condition. To do that, we consider how the Laurent condition can be described using the natural parameters if the target rank is more than 1. Recall the theta representation of the Lancôme condition. The tensor was rank 1 if and only if all the many body theta are 0. Let's do more expansion of the theta representation, focusing on each axial direction. This is mode 1 expansion, mode 2 expansion, and this is mode 3 expansion. In these matrices, there is row of zeros expected for the first row and the first columns. We call these sequences of zero as a bingo. When the rank of the tensor is 1, one row is constant multiple of the other rows. The first row and the first column have a special meaning because they are scaling factors. We can say that if there are a lot of bingos, the rank is reduced to 1. So we imagine that the number of bingo is related to the rank. Indeed, this guess is correct. For example, if there is no bingo in the third row of mode 1 expansion, the tensor's Tucker rank is at most 233. That is, reducing the rank of the tensor to 233 is a projection onto a subspace with one bingo in the mode 1 direction. More generally, we show that if the mode K expansion has BK bingos, then the rank of the tensor will be reduced by BK. Let's see an example of Tucker rank reduction of 883 tensor. Using our proposed method, we will make a tensor whose rank is less than 583. The natural parameters on the purple panels can be any values, and the natural parameters on the white panels are 0. Firstly, we have to make 3 bingos on the first mode expansion since 8 minus 5 is 3. Then we project the tensor onto the subspace, which has these 3 bingos. In this projection, the shaded area do not change their values. Then all we have to do is just rank 1 reduction in each bingo block. We replace this subtensor with a rank 1 tensor using the best rank approximation formula. Then we get a tensor whose rank is at most 683. Next, replace this subtensor with a rank 1 tensor using the best rank 1 approximation formula. Finally, we get a tensor whose rank is at most 583. The obtained tensor is the best tensor in a randomly specified bingo space, but there is no guarantee that it is the best approximation for the entire tensor of the 583 rank. This is because the fact that bingo is low rank sufficient condition and the location of bingo is arbitrary. If we want to reduce the second Tucker rank by 1, make a bingo in the moderate direction and apply the best rank approximation. Okay, we compare the performance of LTR and gradient-based method. The red line is for proposed method. In A, we made a large tensor and we gradually increase the target rank after the approximation. In B, we made a various size of input tensor and reduced these tensors rank 10, 10, 10. LTR is faster with competitive approximation of performance. We obtained a similar result with real data sets. Now we have covered with how we perform Tucker rank reduction. So we can now move on to the second topic, NMF with missing values. In some tabular data, we can find some missing values. We want to do low rank approximation with missing values. As a treatment for missing values, we optimize the weighted cost function. We propose faster rank 1 approximation method with missing values. This slide shows the key idea of our method. We focus on non-relationship between two tasks, NMF with missing values and non-negative multiple matrix factorization. We can find a closed analytical form of the rank 1 NMF. Then we utilize the formula for NMF with missing values. Firstly, we discuss the rank 1 NMF. In some situations, we want to decompose multiple matrices that share factors. The task is called non-negative multiple matrix factorization, NMMF. In the same manner as the first part, we have the closed form of the globally minimized cost function defined with scale divergence. By the formula, we can find the most dominant pattern in X, Y, and Z rapidly. We will briefly introduce how we found the formula. As the same way with the first part of this presentation, we made a mapping from input matrices X, Y, Z to a DAG. We concatenate these matrices and make a DAG, and we define the log linear model on this DAG. Now, since we have a model to discuss NMMF, we focus on the rank 1 decomposition. We say that X, Y, Z is simultaneously rank 1 decomposable if and only if it can be written as a canonical product of shared vectors. We can describe the simultaneous rank 1 condition using one body and two body parameters defined in this figure. X, Y, Z is simultaneously rank 1 decomposable if and only if its all two body theta parameters are 0. We can convert this condition into eta condition. So we can understand the rank 1 NMMF as a projection onto the E-flat subspace with these conditions. As the same way in the first part, using the fact that in projection does not change one body eta parameter, we obtain the projection destination in the closed formula. This is an overview of the proof of the closed formula of NMMF. Now we have seen the sketch of the proof of the formula. Then we move to first rank 1 NMF with missing values as an application of the formula. Our method is based on two basic facts. First, NMMF can be viewed as a special case of NMF with missing values. Second, a factorization after current permutation can be reproduced by permutations after the factorization. Based on these facts, it seems that we can develop the following algorithm. First, we get the missing values in the corner by permutations. Then use the formula of rank 1 best rank 1 formula of the best rank 1 NMMF. And finally, we depermutate it. But as we can see, the first step is often impossible. These are example matrices that permutations cannot correct missing values into a corner. To handle them, we add missing values so that we can correct them in a corner. It is clear that the information in a matrix will be lost, so the reconstruction error might be worse, but since we can approximately solve the task by the closed formula of NMMF, we gain in efficiency. I should comment on when this strategy is effective. It is if the missing values are evenly distributed in each column, we need to add so many missing values, which is bad approximation. On the other hand, if the missing values are heavily distributed in certain lower columns, we do not have to increase so many missing values, which is better approximation. Actually, in some real data sets, missing values are often located only in certain columns. In these data sets, our strategy works well. Okay, so this is an algorithm of proposed method. We increase the number of missing values and correct them in a corner by permutations and use the formula of rank 1 NMMF. And finally, we depermutate it. Okay, so we examined the performance of the proposed method on real data sets with missing values. The baseline is KL-weighted NMF, which is based on gradient method. As you can see, the final column, the proposed method is always much faster than the baseline. When the increase rate is 1, we do not have to add missing values. Thus, the obtained solution is guaranteed as a global optimal solution. When the increase rate becomes large, since we add missing values, the reconstruction error becomes worse. Okay, then the main parts have been finished. Before I conclude my talk, let me share some theoretical results. In the second part of my presentation, we add missing values to solve rank 1 NMF with missing values. After we add missing values, the rank of weight matrix is always 2. The weight matrix is binary matrix, and it indicates the location of missing values. So now we have a natural question. If the rank of weight matrix is 2, can we solve the rank 1 NMF exactly? Can we solve the NMF without adding missing values? The answer is no, unless we use the formula of NMMF for 3 matrices. But actually, we can discuss the generalized NMMF. This is NMMF with 4 matrices. At the same way, with the case of 3 matrices, our discussion is the analytical form of rank 1 approximation. And the NMMF is also equivalent to NMF with missing values described here. In addition, we prove this statement. If the rank of the weight matrix is less than 2, we can correct missing values and transform the input matrix as this form. And then we can exact solve the task by a permutation and the closed formula. Note that the rank 1 NMF with missing value is NP hard to minimize Frobenius norm. But our strategy can find the exact rank 1 solution which minimizes Kerr divergence if the rank of the weight matrix is less than 2. Okay, it was the first topic of theoretical remarks. The second one is connecting to matrix balancing. Matrix balancing is a transforming of a matrix into a doubly stochastic matrix whose sum of each column is fixed. Actually, we can describe the balancing condition using one body eta parameter. So the matrix balancing is a projection onto balanced subspace whose one body eta satisfied this condition. Let's impose the rank 1 condition at once. As a result, since all of parameter of the matrix is identified, the balanced rank 1 matrix is unique. So we can say the cross point of rank 1 subspace and the balanced subspace is a singleton. We can prove that cross point is uniform distribution. Okay, this covers remarks, and just allow me to conclude. We captured the data structure using DAG and made a mapping from data to probability and actualized the projection theory of information geometry. As a result, we propose a faster method for Tucker rank reduction and rank one NMF with missing words. Thank you.